Okay. So let's have a look at a typical structure for a card like this, and let's draw out. So here I can see that there are sort of two main nouns, a bagel and a basket. This might be familiar, given that we've already existed in this domain before. So my first class is going to be, I'm going to move this over a little bit so we have more room. Class, let's just say collaborator. Not leaving myself any space, but let's say here, and then responsibilities below. Responsibilities, there we are, good morning. Looks like I had far too many eyes, but I think that's correct. Responsibilities, yes. Okay. So this one is going to be for a bagel. And what information from these three sort of stories can I think about the responsibilities here? It looks like it needs to know about what type it is. I'm looking at the second user story here. What type? So here, does it need to collaborate with anything? Not really. So it's probably about as far as I need to go with this card. Quite straightforward at the moment. Doesn't need to know about anything, just needs to know about its type. So let's add in the second card. So for this collaborator, this is going to be for my basket. And what does my basket need to know? Well, it needs to be able to add a bagel. So you can say add, and therefore it needs some way, it probably needs to interact with the bagel somehow. If I'm looking up here. And on the third one, I want to be able to get a count of the number of bagels. So there's going to be some kind of count of, I guess, bagels. And we have to interact with the bagel. So here's a fairly straightforward, very simple example of trying to set out some responsibilities, a class, and like how they're going to collaborate with each other. The important thing to note here at the moment is bagel doesn't need to know about anything, whereas the basket needs to know about bagels. So when we use this information, then we have to think about, well, how are we going to structure this in our database? I'm going to move this up slightly. Go from here. What kind of information, if I needed to have or persist this data in a database? Well, let's move from here to some tables. And let's have a table here and a table there. So as you might imagine, for a table, we'll need some kind of primary key. Primary key. Primary keys are almost usually always IDs. Not always, but usually. 99% of cases. An ID that the database will auto increment and keep its responsibilities to make sure they're all unique. So if we had an example here, we would be able to do something like an ID of 1. We also need a second column, type, to be able to store that information. And let's say, for example, this is going to be an everything bagel. So far, so good. see a thumbs up. Okay, so that's about enough that I need to. What about my basket? What is my basket going to look like? What information do I need for my basket? Well, let's begin with the same way. Let's call this the bagels table. And let's call this the baskets table. I need another ID. And let's say this is going to be ID of 1. Any other columns that I need? Anyone want to shout out if I need any other columns?
Will it need a column for bagels?
Okay, let's have a look at that. What would be inside this column?
Would it just be the IDs?
And how would you list them out?
In an array.
Okay, so here is a question. What's the problem with this? So what Anthony is trying to suggest here is a way to find a way to represent how many bagels that this basket has of ID 1. We have to find a way to represent this. And the suggestion here at the moment is to have a column in the baskets table that represents the list of arrays, thinking quite closely to having an array within the class instance that we've been doing so far. Can anyone spot problem with this? Or think about it, reason about this?
I don't, like, maybe the problem would be access, but I was going to say my thoughts would maybe have the different types of, like, have a bagel with each ID and then have another column of owner, and then you could just look by owner and then work out.
Cool. Okay, so we have 2 suggestions here. We have Anthony's approach and Josh's approach. Let's make it personal. I'm joking. Okay, so here's the classic approach that when we first encounter relational databases that we think about. Storing arrays is very hard to do within a column. Usually we'll have to find a way to turn it into a string and then do a lot of parsing. So sort of manipulate the information here. And this is not how we store an associated bit of data. Instead, we keep the information in this table, not under, as Josh suggested, as like some kind of owner, but the name for this is some kind of foreign key that relates to another table's primary key. So let's use the sign notation is do something like a basket ID and say which basket does this a bagel belong to. This bagel, for example, let's say it belongs to basket ID number 1, and this maps across to this ID. So this is what we call a foreign key. The reason this is important is because it's usually the inverse of the CRC up top. The collaborators over here for the bagel, but we represent that information in the bagels table, not the baskets table. And that's usually a gotcha whenever we think about trying to infer information or infer structure, is that we present that information in the bagels table. So let's add more information in to see how this would stack up. So we're not going to include this information here. I'm going to get rid of that there. We actually don't need any more information at the moment about our baskets table, given the current requirements. So imagine we had a couple more bits of data here. Imagine we had 2 baskets, ID number 2. And let's say we had 2 more bagels, ID number 2 and 3. And let's say this is a plain bagel in the same basket, ID 1. And we had another bagel, back to an everything bagel, in the second basket, therefore ID 2. And so here we have a concept of a primary key and a foreign key. A foreign key in a table does a lookup on a primary key of the corresponding table when we need it to. So if you wanted, imagine an SQL query along the lines of find me all of the baskets, find me all of the bagels in basket ID number 1, it might look something like this, where we have a select everything from bagels where, if we knew it straight away, where basket ID how we want to prescribe it, it should be all lowercase, but for some reason writing one in capitals, pseudocode, it's not actually accurate, fine. So everything bagels but is equal to 1. And it would look up the basket ID here and find me those ones. And it'll give you a list of just ID 1 and 2 for the bagels. This is not talking about joins, where we would do a different kind of select query where we join the tables together, but we're not going to talk about it just now. This is just trying to focus on primary keys and foreign keys. Okay, questions and thoughts about this translation from these requirements to the cards to the tables?
Can you have like infinitely many foreign keys?
You can, yeah. That might suggest bad database design if you have one like God class or one God table that you always relate everything else to. But technically, yes, you can.
What would go in the baskets table other than just the basket IDs?
What requirements are you thinking about?
I guess I actually wasn't. It just looks very bare, so I would expect something else to go in it apart from just the IDs.
And what would you, given the requirements, what would you expect there to be?
Yeah, thank you for zooming in. Couldn't see.
I know it's quite small.
I guess the bagel count, like the total amount of bagels in the other table.
That's a really interesting question, Suzanne. So Suzanne's suggestion is like, can we keep the count of the bagels? So let's have a look at what that would look like. We would have a count here. Say, for example, it is currently at 2 and 1, correct? Yeah. So what happens when we create a new a bagel and add it to a basket? We create a new bagel. Imagine we create it straight away and create the association. So let's do bagel number 4. This is a color convention, please, Edward. 4. Let's say it's a sesame bagel. And we're going to put it in number 1, because number 1's on a shopping spree. What do you now notice?
They're out of sync.
Yeah. So if you keep the count, you'd have to then make sure you do an additional operation to update the count. So every time you add a bagel, you have to go to your baskets table and update it. So not just one create, you'd have to also update. So it's possible. But this is an interesting question because we don't need this. This is not the source of truth of the count. The source of the truth of the count is on the left in the bagels table. So if you need a count, rather than store it in a database, store it as a functional a procedure that you can run whenever you need to. So you would have in your model, you could write when you're in your sort of application code, you could just simply ask for count. That would send a query like this to get at all of your bagels and return a number. So you don't actually need to store the count in the database if you need to produce a count.
So in that case, would you even need a separate table for the baskets?
If you want to be able to distinguish between which bagels are in which basket, you might just get away with having like an ID like this to differentiate them, and so it wouldn't be a foreign key. But the purpose of this exercise is to demonstrate how you would relate two tables. All right.
Okay, cool. That makes sense.
Yeah. Now, the question that you're posing is also interesting because maybe there does need to be a update process because that information is critically important here, and we need it to persist for some reason, and then we'll have to do some reconciliation at every single point in time. So there might be some use cases that would need you to have it. So this is always about what are the requirements and do we need it? Where possible, we want to keep, as always, minimal state. Keep as minimal things as possible, and if you can calculate it at runtime, do so. What is the minimum amount of information that you need to persist? Cool, good question.
I had a question.
Yes.
So when you select the bagels from the basket,
yeah.
How does the bagels table know about the baskets table just because it has the foreign key in it? And if it didn't have the key, then it wouldn't know what the baskets table is.
Yeah, at the moment here on this select query, it's just looking at this column, and we're not doing any joins yet. So if we needed to join a table, it would add this information to the table. I don't want to talk about joins just yet. I want to talk about it on Tuesday. So if I did a simple select query that you see at the bottom of my screen, I don't need to worry about the baskets table. That information is already in my bagels table. It just looks at the ID. Yeah, no, it's going to be too. It's going to have to explain a little bit too. Maybe I'll do it. I'll explain it. I'll show it. I may not explain it right now. Another way to do this would be to do a query like this when we do select everything.
Can't see what you're typing.
From bagels. And we're going to join baskets on, and then we have to provide the foreign key. So we're going to do ID is equal to basket ID, and this is going to be, hold on basket ID. So it's going to take this as the foreign key, and this is the primary key of the basket table. So this is from the bagels table, and this is from the basket table. And we join those two bits of information together, and then we can use it and do something like where basket ID is equal to 2 this time. So this is a query where I'm drawing the tables on the keys and asking for the basket ID where it's 2. So this allows me to join tables together based on the keys and adds the table. So it joins the table, and so you'd actually end up something like a large table. Let's say we have all those 4 bits of data, 1, 2, 3, and 4. And
I can't see what you're typing there.
I know, calm down. Everything, what do I have up here? Plain, everything, plain, No, sesame. And then we had 1, 1, 2, 1, 1, 1, 2, 1. And then we add the information to the table. So this is going to be the basket ID would be again 1, 1, 2, 1. So let's be explicit. If I zoom in here. So when I do a join, this is what the table then looks like after I've joined them together. So this is the ID. And let's say this is bagels.id. This is bagels.type. This is bagels.basket ID. And this other one is basket.id. You can read my handwriting there, apologies. So this is what the table looks like after you join it together. It adds any information onto it according to it. So you'll see the basket appear multiple times because it's joined it on these two things. There's a match here between these two things. So imagine if that's what the join does. It joins it here. And then if imagine you had like a name for your basket or an owner of the basket, it would add that information here. So imagine it was like Edward owns basket number 1 and Susanna owns basket number 2. It would just add that information here. So this would be the table, the joined table at the end of it.
What do you like? I'm going to phrase. What do you achieve from joining the tables like that?
And the ability to associate different bits of information. So the first problem we encountered was how do we store relationships? How do we store what bagels are in a basket? And so rather than store them in an array, we have to separate them into 2 tables. So one of the things that we're trying to do here is, a second example is like, imagine you had a bunch of employees with company addresses, and lots of employees have the same company address. Rather than always write out the same company address, you want to just associate it with one record in an address table. So this is a process called normalization. We want to sort of reduce the amount of repeated data in a table. Yeah. So like in this case, rather than always have to write out Edward, Susanna, and Edward, if I had one table of like who is the basket owner, all I need to do is represent it by the basket ID. And so I'm reducing the amount of repeated information in my 2 tables. And this one table otherwise would become huge, and I'll keep adding loads and loads of columns and lots of and having a lot of repeated data. And imagine this at scale where you have like, I don't know, 100,000 to 1 million records in a table, you would have a lot of repeated data. And so we're trying to normalize it by extracting the same process that you're doing before, keep it dry, let's modularize, let's move things out, same process, same idea here. Let's find the repeated stuff and bring it out in a separate table and relate it by an ID. That's a good question. Now, when we need to query it, we join them back together based on these keys, so we can find the associated bits of data.
So would you have to join the table every time you write a select from, or would you just join it once and then you can use it?
You would join it temporarily whenever you need to make a query to it. So joins, that's why some queries, if you have lots and lots of data and lots of tables, can sometimes take up to 2 minutes to run. You have huge amounts of records and data, and a lot of complicated joins. You can get some like awful queries to have a look at, which do like complicated joins. It takes you ages to read through. But we're going to keep it simple for the moment. So what you're looking at here is a relationship, specifically a one-to-many relationship. A basket has many bagels. That's the kind of phrasing or the terms that you'll hear a lot. And in the inverse relationship is a bagel belongs to a basket, a one-to-many relationship. And you'll see this sort of like you'll hear it spoken about that way, and you'll also see it sometimes modeled where you have like a line and like an arrow like this. Where this is a one-to-many. This is the bagel. No, this is the basket. And these are the bagels. One-to-many. Cool. So this is our first kind of type of association that we're going to have a look at, one-to-many. I'm going to split you all up into pairs, and you're going to have a look at doing this for yourselves for these stories. So read through these stories, create your cards that you need to, like I did. Try and think about what responsibilities do they have, what methods or bits of data they need to be responsible for, how they're going to collaborate, and then do your cards and then your tables. Let me create spaces for everyone because we're going to do it on Miro. And let's make them big so you have enough area to play around in. And we need 7. Feel free to move these around if you want. 3, 4, 5, 6, and 7. Actually, I'm going to lock them all down because that's going to be easy for everyone. Okay, we have 7 spaces for you to do some work on. Read through the stories, create your cards, and then create your tables, and then we'll have a look together on what we've decided. There's also going to be a many-to-many relationship. So have a look at the associations here and maybe have a read through, but I'll talk through the many-to-many at the end. But we should be able to get far enough so far. Sound good? Any thoughts and questions before I split you all up? Okay. Opening rooms. Recording. Look at that. Yeah, sorry about that. I should have clicked resume a while ago. Students, cohort, start date, end date. Okay, and I want this data to be something like, when do we start this cohort? It was like March, right?
March 1st.
2 months. We've been doing this for 2 months, have we? Christ. Okay. Let's just say something like 2021 March, which is 03 and 01. When do you finish? I should know this. 21 is like June 4th, right? Okay. Start date, end date of cohort. So I can learn students' names. I want each student's name to link to the URL of a picture of the student. So a student needs to be responsible for a URL. And so let's add that in. Let's choose a different color. Let's go this color. URL. And let's say, for example, it's going to be like www.pic.com, pic.jpg, let's say. Because clearly that's a valid URL. Fine. That's the URL. Ostensibly, we could try and extract that out to some kind of table that has like assets and just like have different pictures and things like that. Might be worth it. At the moment, I don't think I have enough information to justify that. It's just a URL, so I'll probably keep it here. If I needed more URLs per student, I would then extract that definitely. At the moment, it's just like a name. So I'm going to keep it here for the moment. URL for a picture of a student. As a coach, so I can mark certain students, I want to tag a student with many named tags. So let's create a tags table. And this is going to be with an ID, and this is the tags table. Color tags. And what do I need it to have? Named tags, again, like a name. Let's give this an example. I want ID of 1, and this tag is going to be what's non-controversial? Happy. Okay. I want to tag a student with many name tags, so I can see students with the same tag. I want to filter students in the list by name tags. Hey, so in order to, why can't that work? Move. Let's add another student. Lewis, first person I see. Second, Lewis. You're in the same cohort. You have a picture as well. Strangely, it's the same picture. So both Marie and Lewis look exactly the same. In the same cohort, I need to add anything to that table. And I also want you to be happy. All right, so I'm going to have one tag for both of those students. So that's interesting. How am I going to present that information? But I also maybe want Lewis, you're not just happy, you're also what's another tag? Let's just say good. All right, morally. All right, morally good. How am I going to present this in this relationship between students and tags? If Lewis, you are both happy and good, but Marie, you're happy. So for this, I need a separate table to hold this relationship. So I'm going to keep my tags there. I'm going to keep my students, but given that I now have one student can have many tags, but a tag can also be applied to many students, this is what we call a many-to-many relationship. So for that, I'm going to use another table. And this is going to be my sort of students and tags table combined. And here, all the information I need to do is just the ID of this. It doesn't specifically actually need an ID, but let's use one. And I want the two columns here. Why are my tables slowly rising? They're like half of them off the page. They're going to be the student ID and the tag ID. So this will be presenting the information about the relationship between a student and a tag. So for example, I would have a relationship between Lewis and the two tags. So the Lewis is ID 2, student ID 2, and the tag for the first relationship is 1. But let's have another relationship, same student, but different tag. So Lewis has both those tags, whereas Marie, sorry, there should be 2. The second relationship. So let's add a third relationship. This is Marie's student ID number 1, and Marie, sorry, you're not morally good. I haven't yet been able to give you that tag. You're just happy. So let's give you that tag. So this is how thumbs up from Marie. So this is how we're going to present this information. It's a many-to-many relationship. This is important because I don't want to repeat my tags. I've got 2 tags that comply to many students, but a student can have many tags. And we keep that relationship separate in a separate table, in a joined table between students and tags. As a student, so I can reflect on my days, I want to rate each day out of 10. So this looks like it's going to be another table. We're running out of colors. And I'm going to break the convention and put it exactly within the bounds of my whiteboard. There we are. Can we still see that? Yes, we can. So this is another ID column. This is going to be my ratings table. And here, what do I need to have? I need to have some kind of score. What else do I need to have? Each day. So I'm going to maybe just have like a created at timestamp that tells me when it's created. So I can get an overview of feedback. I want to see an average of the day ratings for each student. That's fine. I can calculate it when I need to. So here, for example, imagine a rating needs to belong to a student. So I need another column to represent who's submitted this rating. So I'm going to add a column here for a student ID. So let's fill in this data with some representative information. Let's say, Marie, you're having a real peach of a day, so you scored this out of 10. You created it today, so it is 2021 0430, and you are number 1, ID number 1, yes. Whereas Lewis, you object to being called morally good. So really, you've had a score of 4 today. Same date, and your ID number 2. The average of the day ratings for each student, I should be able to calculate just by looking at all the ratings for a certain student on a certain day and then doing an average. I don't need to store that in the database. That's all calculated data. I store the sort of the raw information, the minimal where possible in my database. Anything else I can calculate. So this is, I think, a representative a domain model that would show a schema that could support all these requirements. Thoughts, questions?
So the student ID, you've put in student tags and the ratings tables. Is that literally the ID that was in the students table?
Yep.
Okay, cool. I didn't know if you'd have to do like a separate ID for that, whether you could just take from that primary key.
So all the cohort ID, student ID, tag IDs, they're all foreign keys for their respective tables' primary key. Any other thoughts and questions?
So just to clarify, the student tags table is the many-to-many relationship.
Yeah, correct. This is the information that this is the way to present that relationship, many-to-many. We create a tags, we create a students table, and we get a third table to store that relationship information.
Okay, thanks.
If you want to think about it, in a way like this, so far we have 2 tags and 2 students. This is 1, this is 2. So we have at the moment these two here and just this one here. For example, I'm not sure the numbers are exactly correct, but let's say this is the students, and this is the kind of information that we need to store, a relationship between the students and the tags of the different information. So I need 3 rows essentially. I need to store this as a row in my table, this is a row in my table, and this is a row in my table. And that's why we're creating a 3rd table to store that information. So we have a students table, we have a tags table, and we have a table to hold the red lines, the relationships between a student and a tag. Yeah, cool. Many to many. Otherwise, also seen denoted like that in Unified Markup Language, UML. Cool. All right. Last few minutes for any questions or thoughts as resulting in this exercise. We're thinking back to our objectives here, which is explain how to use these cards to model a domain, thinking about nouns and verbs and any collaborators, model using these cards, and then use those cards to infer a database structure. Any thoughts or questions?
Yeah, I've got a second question. I thought I'd let other people have a go. So with all these different tables, how does that affect, like, because you could end up like with a bigger database, you could end up with loads and loads of tables. Does that affect like the speed of your app or whatever when it's trying to access all these different areas that it wants to go to for different bits of information?
The inverse. Well, it's not about the number of tables. It's about how normalized your data is. How quickly can you fetch a piece of information without having to look through so many, like one huge table. The speed of looking through a million records in one table is longer than quickly finding your way through joined tables. Especially when you're trying to search for, I don't know, a column, data in one column. If it's repeated a lot, it becomes hugely expensive. So the number of tables doesn't matter, and you actually end up finding you need less data the more tables that you have, because you remove the duplication. The complexity arises, as we found in when we're thinking about sort of modularity in object design, is in readability, or the ability to understand so many different tables rather than always looking at one table. But that's something that will get easier with time.
How do you know when you're, without experience, how do you know when your tables are good design now and for the future, without like having inputted a load of data and then having to migrate it if it's trashed?
Yeah, rule of thumb is the duplication. Can you spot any repeated data? If you can spot repeated data, like the same things cropping up that you have to do, or when you have to update something, you find yourself having to update lots of different tables. Those are signs, like code smells. These are sort of smells in the design of your database. If you find it difficult to implement any application code that you need to, it might be something with your database design. As long as we're thinking about relational databases, storing data in this way. We haven't thought about non-relational databases, which don't use sort of table structure like this. And we'll do that next week, at the end of next week. A short session, because we're not going to spend too much time on it. What other things can you do to think about the design at the moment? Repeated data is a big one. Otherwise, what other things do I look for? That's the biggest one really at the moment, normalized data. And there'll be other things about how quickly to things like indexes. How can we speed up searches by adding indexes on certain repeated columns or searched columns? But we're not going to worry about any of that stuff at the moment. So for the moment, I just want you to think about, when you think about your design, is am I repeating any data in my tables? If I need to update information in my tables, can I only update one place? If I need to update more than one place, that should be a sign that there's some more normalization you can do. All right. Yeah, good question. I like that question. All right, let's wrap there. And thanks for this morning for the focus. Some nice designs here, and hope that was helpful thinking about it. The reason we're doing this now is because part of the project for Bookmark Challenge is essentially what you've just been thinking about, which is comments, a one-to-many relationship. A bookmark needs to have many comments. And then tags. Bookmarks we've just done. Bookmarks have many tags, and a tag have many bookmarks. So this gives you sort of a framework to think about how to represent this information in the database. The missing part here is, how does SQLize, how does our ORM help us do this? And so we're going to cover that on Tuesday morning. All right. The docs are all there if you want to have a go at it with your pair partner this afternoon or over the weekend, but we're going to focus on the implementation side of this on Tuesday morning. All right. We'll do that on Tuesday morning, and then we'll think about user management as well on Wednesday and Thursday. Cool. I want to give you some time this morning, so let's wrap there, and I'll see you all at 2:20. Bye, folks.
Ed, do we have a meeting at lunchtime?
Ooh, thank you. Yes. Let me just stop that recording because your question's been asked, but we're going to shut the recording off before I answer it.